This is problem 16 from chapter 14. We have a small box of mass m given a speed of the square root of 1/4 times g times r at the top of the smooth half cylinder, and we want to determine the angle theta at which the box leaves the cylinder. So when the box leaves the cylinder, that's when it loses contact with the surface of the cylinder, so N, the normal force, is equal to 0. It's a smooth half cylinder, which means there's no friction, and R here is the radius of the half cylinder. I have my equation here, which is the one that we've talked about before, and I put it on my equation sheet, except that because we don't have any springs, I just didn't bother to write the elastic potential energy. So I can go ahead and plug things in to my equation. I have the initial velocity, so this is 1/2. The mass is just m, so that's still m. And squaring the initial, well, it's the initial speed, just gives me g times r divided by 4. Plus the initial gravitational potential energy. I'm going to choose the gravitational potential energy to be 0 at this height here. So initially, the gravitational potential energy is m times g times h1, which is the distance from here to, it should be the center of the box. Later on in this book, we are going to worry about the size and shape of an object, but we haven't quite got there yet. And so I should be going from here to the center of the box, but I'm told it's a small box, and I'm not given the dimensions of the box. So if I was, I could say from here to the center of the box would be the radius of the smooth half cylinder plus half the height of the box. But because I don't know what the height of the box is, and since it's a small box, I don't really care what the height is, because I'm assuming that this distance is going to be much, much smaller than r, so it's not really going to make a difference. We're just going to say the initial gravitational potential energy is m times g times r. Okay, now I suppose we should draw a free body diagram for the block. And this is at some point between here and here. I have no force of friction because it's a smooth surface. I do have a force of gravity acting downwards. However, it doesn't matter when I calculate the work because I've already included the gravitational potential energy, so I don't have to worry about this. This is the forces other than gravity. So what's touching the box is the cylinder, and it exerts a normal force. However, I have a dot product here. That normal force is perpendicular to the surface of contact. But if the box is sliding on the surface, it's going to be moving parallel to the surface of contact. So dr is perpendicular to the normal force. So the work done by the normal force must be 0 because the normal force is perpendicular to the displacement. Now, that is often true. It doesn't have to be true, but if you have an object sliding on the surface and the surface is at rest, then the normal force should be perpendicular to the displacement. One exception to this that I can think of is if you had a box sliding on the floor of well, it doesn't even have to be sliding, but if you had a box on the floor of an elevator, so then you have a normal force acting upward, but the box itself would be moving with the elevator, so either upward or downward, and then the normal force and the displacement would be in the same direction. So it's not always true that the normal force doesn't do any work, but if the object is sliding on the surface and the surface itself isn't moving, then we get 0 for the work done by the normal force. And I do not know what the velocity is when the box leaves the surface of the cylinder, so I just leave that velocity as v2. And I don't know what height 2 is, but I can write it in terms of the angle theta that I have. So, and again, ignoring the dimensions of the box, I want this height here, this height here, so that's h2. I know that this distance is the radius. Maybe I should draw more of the cylinder there. Okay, so this distance is the radius, so I want this height here, and this angle is theta, so from here to here would be r cosine theta. Okay, so this is plus mg r cosine theta. I'm looking for theta, so, well, even though I'm looking for theta, I think first I'm going to have to find this velocity. So, I think I'll just go ahead and solve this equation for v2, even though it's theta that I'm trying to find. So that just means I bring the mgr cosine theta over to the other side. So I have, what's this now? 1/2 times 1/4. So that's 1/8 times mgr plus mgr. And then bringing this mgr cosine theta over to the other side, we can combine it with this and say mg times r minus r cosine theta is equal to 1/2 times the mass times v2 squared. Now let's divide everything by the mass, so that cancels out, and then multiply both sides by 2, and then just write it with the v2 squared on the left-hand side. Multiplying by 2, and we could simplify it even more by pulling out a g and an r from everything. So 1/8 times 2 is 1/4. Then this would be, pulling out the r, that would just be a 1. Oh, but I'm supposed to multiply it by 2, right? So that would be a 2. And that would be pulling out the r and multiplying it by 2, minus 2 cosine theta. Okay, so let's just leave it like this for now and think about how we can find what theta is. I can't do it unless I can find the velocity when the block leaves the surface. Now there's one piece of information that I haven't used yet, and that is that the normal force is equal to 0 when the box leaves the surface. And the normal force didn't come into this equation at all because it doesn't do any work. But I can use that piece of information to find the velocity when the box leaves the surface. So the only forces that would have come up here are the ones that are parallel to the displacement. So now I'm going to look at the forces which are perpendicular to the displacement. Well, I already have my free body diagram here. So I have the normal force, but I want to take the force of gravity, I want to break it down into components. I want to break it down into a component that is parallel to the normal force and a component that is perpendicular to the normal force. And this angle here was theta, which means this angle here is theta, which means this angle here is theta. So this would be mg cosine theta, and this would be mg sine theta. Okay, so now I want to look at these two forces, and this is in the direction that the box is moving in, which is the tangential direction, and this is in the normal direction. And I know that when an object moves in a circle, I must have acceleration pointing towards the center of the circle, and that's v squared over rho. So I have the sum of the forces in the normal direction is equal to the mass times v squared over rho. So I want you to remember that when you're using the work-energy relationship, if you have a force which is perpendicular to the displacement, it doesn't come into this equation at all. So what that means is sometimes you actually do need to consider those forces, which would be looking at the sum of the forces in the normal direction here. So sometimes we need to use that along with the equation that we have here. So for me, that in this problem, that would be mg cosine theta pointed in the positive normal direction minus the normal force is equal to m times v squared over the radius of curvature. When the box is on the surface, that would just be r, the radius of the cylinder. Okay, now when the box loses contact, the normal force goes to 0. So this is mg cosine theta. This is the angle theta that we're looking for. And this is equal to m times v2 squared over rho, because this is the speed when the box loses contact. The mass cancels out, and now I can say v2 squared is equal to g times r times cosine theta. And now I can take this equation here. Maybe I shouldn't have boxed it because it's not a final answer. We'll circle it instead. Okay, so take this equation here and this equation here and put them together, and we get g times r times cosine theta is equal to g times r times 1/4 plus 2 minus 2 cosine theta. Look how nice this is. That cancels out. I can bring this minus 2 cosine theta over to the other side. That would make it 3 cosine theta is equal to 2 plus 1/4. That would be 8/4 plus 1/4. So that's 9/4. And I'm looking for theta, right? I can divide both sides by 3, and I get cosine theta is equal to 3/4. And finally, theta is equal to inverse cosine of 3/4, which is approximately equal to 41.4 degrees. And that is our final answer.